guys, we're winding down the distance learning school year. So this is our last kind of mini unit, and it's on probability. So probability tends to be one of the favorites because it's something you can actually sink your teeth into, and you make these kind of judgments every day of your life. So as you guys probably know, probability, the definition, is the chance or likelihood an event will occur. And when we express the probability, its value is always between 0 and 1. So 0 would mean there's no chance of that event happening, and 1 would be there's a 100% chance of that event happening. So we can write probability in 3 ways. We can leave it as a fraction, or we can make it a decimal, or we could turn it to a percent. Those are all valid ways to express probability. So when you think of probability, you want to think of some event, the probability of some event occurring out of all the possible events that could occur. So the way I like to think of probability is want over all. What you want divided by the total number of ways that that event can occur. Now the all part, another way of saying that is sample space. So the total number of possible outcomes is our denominator, and the specific event or what we want to happen is the numerator. Okay, so let's talk about sample space for a moment. Our first example, we're going to define the sample space of an event. And in this event, we are going to first flip a coin, and then we're going to roll a 6-sided die. So it's an event with 2 parts. So probably the best way to do this is to make a little tree. So let's think of all the ways that we can flip a coin. Okay, so we have a coin. We can either have heads or tails. So I'm going to write heads here, and I'm going to write tails here, right? So our first event is just, we have a 50-50 chance of getting a heads or a tails. Now what though if we want to have, like, we want to put the 6-sided die, which is basically just a dice, right? A single, if you have a pair of dice, a single cube is a die. So let's think of the ways that this event could turn out. Well, we could roll a heads, and then we could roll a 1 on the 6-sided die. We could also roll a heads and a 2. We could roll a heads and a 3. We could roll a heads and a 4. We could roll a heads and a 5, or a heads and a 6. So these are 6 possible outcomes in our sample space. However, we could also roll a tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, and tails and a 6. So there are also 6 possible outcomes for this. So if I take the 6 outcomes plus the 6 outcomes, I get 12 outcomes in the sample space. Right? So that would be the denominator of our want over all. Right? And then we could define an event, like what's the probability of rolling a heads followed by a 2, right? So, but first we always want to define what our sample space is. Okay, so let's do a problem on actual probability. Okay, so let's say I've got a student and the student randomly guesses on a 4-question true or false quiz. Clearly the student didn't study. What is the probability that she will get exactly 2 correct answers? So let me draw the table. We're going to step this out. So this lesson is really all about introduction. So the answer to is there an easier way to do this is yes. But I want everyone to understand what we're doing when we're using these shortcuts. So let's think of all the ways, all the possible ways the student's test event can come out. Well, she could get 0 of them right. So let's call C correct and I incorrect. Well, there's only one possible outcome if she gets 0 of them right. And that's I'm going to do all 4. She gets incorrect, 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 incorrect. Right? That's the only way to get 0 out correct. How about if she gets 1 correct? Well, how many ways can I get 1 correct? Well, I could get the first one correct and the next 3 wrong. Or I could get the second one correct and the others wrong. Or I could get the third one correct. Or I could get the fourth one correct. Right? So there's actually 4 possible ways for her to get one of them right. Okay, let's talk about when she gets 2 right. Well, if she gets 2 right, that's a little more complicated. Because she could get the first 2 wrong and the second 2 right. She could get the first 2 right and the second 2 wrong. Right? She could get the second and the fourth right. Or she could get the first and the third right. Right? Or she could get the outer one, the first and the fourth right. Or she could get that. Oops, I didn't make my thing long enough. So let's count them up. 1, 2, 3, 4, 5, 6 possible ways for her to get 2 of them correct. Okay, how about 3 of them correct? Well, she could get the first one wrong and the next 3 correct. Or she could get the second one wrong. She could get the third one wrong. Or she could get the fourth one wrong. This is kind of tedious, right, guys? Well, luckily the fourth one, there's only one way for her to get all 4 of them correct, and that's C, 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 C. So let's count up the exact number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. So now that we've done all that, let's answer the question. What is the probability that she will get exactly 2 correct answers? Well, our numerator is exactly 2 correct answers. So it looks like there are 6 ways to get exactly 2 answers. So that's going to be our numerator. So our numerator is 6, and then we went through all the trouble to find the possible outcomes. So it would be 6 over 16. And just like a fraction, I can reduce that to 3 over 8. So I can leave my answer as 3 over 8, or if I want, I could change it to a decimal, or I can make it a percent. Those are all legit ways to express it. Okay, so that's the tedious way to do it. Like I said, today is the tedious way. So our probability of getting exactly 2 correct answers on a random guess would be 37.5%. Okay, we are now going to move over to the next board. Okay, guys, some quick vocabulary for you. If somebody ever asks you to find the probability of the complement of an event, now this complement doesn't mean like saying something nice to someone. The complement of an event is the probability the event will not occur. And here's some notation for you. This is the probability of the complement of the event. So since an event it either occurs or doesn't occur, right? You can't have it kind of occur, right? So I can find the complement by doing 1 minus the probability of the event. Easiest way to do this is to look at an example. Event A is the probability it will rain. Okay, so if the probability it will rain is 0.4, what's the probability that it won't rain? Well, 1 minus 0.4, which is 0.6. Right? It's an either-or situation. Either rains or doesn't rain. Okay, let's look at something a little bit more complex. Let's say I roll a pair of dice. If I roll a pair of dice, there are 36 possible outcomes I can have. Right? So if you're familiar with dice, I could either get 2 1s, which would be snake eyes, right? Or I could get a 2 first, then a 1 second, or a 2 and a 2, or a 1 and a 2. So take a look at that and see, right? So the outcome 2, 1 is different than the outcome 1, 2, right? Because in this situation, the 2 was rolled first and the 2 was the first die and the 1 was the second die. Here it's opposite. So these are all the possible outcomes you can get when you roll a pair of dice. Okay, so they want us to find the probability that the sum is not 6. Okay, so we wonder, why do we even use the complement of the event? Well, in this case, the probability that the event is not 6 is going to be a lot of them, right? The sum, sorry, not event. The probability the sum is not 6 is going to be a lot of them. So I'm thinking, to do less work, what I'd like to do is find the probability that the sum is 6. So let's find the probability that the sum is 6. And I'm just going to circle or underline the ones where the sum is 6. Well, 5 plus 1 is 6. Oh no, that's not right. Oh no, that's right. 5 plus 1 is 6. What else has a sum of 6? This has a sum of 6. This has a sum of 6. This has a sum of 6. And this has a sum of 6. So how many did I underline? I underlined 1, 2, 3, 4, 5 out of 36. Now, they didn't ask us the probability of finding the sum equals 6. They asked us the probability of finding the sum is not 6. But I don't want to have to underline all the other ones. So what I can do is find the probability the sum is not 6 by just doing 1 minus 5 over 36, right? Which would be 36 over 36 minus 5 over 36. So the probability that the sum is not 6 is equal to 31 over 36. So it can actually be useful, the complement can be useful to us sometimes. Okay, let's find the probability that the sum is less than or equal to 9. Probability the sum is less than or equal to 9. Okay, I'm going to erase these marks. Well, that means I want the sum to be 9 or less. So let's underline all the ones that have 9 or less. Okay, this one, this one, this one, this one, this one, right? Okay, did I get them all? 9 or less. Nope. Might have been good to do the complement on this one as well. Yeah, it might have been good to do the complement on this one. So I just underlined all of the ones that have sum of 9 or less. Did I get them all? Yes, I did. So again, it might be useful for us to count the ones where the sum is not 9 or less. So I'm going to circle the ones here. 1, 2, 3, 4, 5, 6. Okay, so the probability of the sum being more than 9 is 6 out of 36, right? So if I count up all the ones I underlined, that's going to be 30 out of 36, which can be reduced to 5 over 6. So it might have actually been useful to do the probability of sum not equaling or being less than 9. Okay, guys, we are now going to do our grand finale. We can also think of probability in terms of an actual physical space, right? So in this case, we have ourselves a dartboard, okay? And the person throwing the dart has 0 talent at throwing darts. The person just randomly throws the dart at the board. So let's think about what this is here. Here, right, I need to start figuring out, need to find the area of the entire figure as my sample space. And then each of these little circles and the outside of the circle is worth points. So if the dart lands in the outside the circle region, you get 0 points. 2 points here, 5 points here, 10 points here. So first thing, I know that all of these little pieces are each 3 inches long. Okay, so I can then make an assumption that the radius of the circle, which is right here, is 9 inches. Right? And then we know the radius goes from the center of the circle all the way to the edge of the circle. So that means I can also infer that this is 9. So what does that mean about the side of the square? Well, I know the side of the square is 18 inches. So what they want to know is, am I more likely, if I randomly throw the dart, for the dart to land in the 10-point region, which is this right here, I'm going to shade it, that's 10 points. Or is it more likely to land in the 0-point region, which is out here? So what we want to do is we want to find the probability that if I randomly throw a dart, it lands in that 10-point region. So let's think of what we want here. We want the probability of the dart landing in the small circle okay, that's what we want. That's for 10 points. So let's think about this in terms of the figure here. Well, we want, if we're looking at the space inside the circle, we're thinking of the area of the circle. So to find the probability of it landing in the small circle, we want the area of the small circle divided by the all. And in this case, the all is the square. Okay, now we got to remember our geometry. So we know that the small circle has a radius of 3. A radius of 3. And the area of a circle is equal to pi r squared. So the area of the circle is going to be pi times 3 squared. And then the area of the square, right, is 18 squared. So what is our probability of 10 points? It's equal, of the dart landing in the small circle, it's 9 pi divided by 18 squared, which is 324. And we all know pi is a number. It's not a variable. It's 3.14. It's there on your calculator. So you can just plug it on into the calculator and you get 0.0873. Or we can think of that as 8.73%. So that's your likelihood of getting 10 points. The probability of getting 10 points is 8.73%. Okay, not super likely. Let's look at the probability of getting 0 points. That's harder because here we had a defined shape, a circle, right? But what we need to do to get this green area here is we actually have to subtract, right? Would you guys agree that this square minus the big circle is equal to this leftover green space, right? So if I want the probability of getting 0 points, what I need to do is I need to take the area of the big square, minus the area of the big circle. Right? That's what I need to do for my want. The area of the square minus the area of the big circle, all divided by the whole figure, which is the area of the square. This one's a little harder, right? Because this shape, this is not a meaningful shape in geometry, this green area. Okay, well, let's start doing this. We know that The area of the square is 18 squared. What's the area of the biggest circle? Well, look what we have here. The radius of the biggest circle is equal to 9. Right? So I can say that's equal to pi times 9 squared. Right? Okay? And then it's divided by the whole figure, which is 18 squared. Okay, let's simplify this then. 18 squared, we know up here, we got 324. Now if I do 324 minus 81 pi all over 324. And you can punch that into your calculator. When you do, make sure you've got parentheses on the top. So when I do that, I get 0.215. So what is more likely, guys? 0.215 is 21.5% chance you will get 0 points. So unfortunately, the probability that you're going to get 0 points is more than the probability you're going to get 10 points. It usually works that way. All right, guys. That's it for chapter 10.1. I'll see you for 10.2.